It's good to see you folks again. We're going to begin this morning, as we normally do, with a retrospective on what we've seen yesterday, and then talk a little bit about what's coming down the pike today. Yesterday, we completed our survey of the basic building blocks of the core logic associated with agent-based models and any logic. Specifically, we initially looked at implementing an open population. We did so in a simpler fashion than we had worked with the previous day. This open population model allowed us to capture immigration, mortality, and birth processes, and also provided us a bit of a glimpse of some additional features associated with any logic. For example, the capacity to define custom distributions. Distributions, for example, returning, allowing us to sample agents based on some distribution, or excuse me, sample ethnicities based on some distribution of encountering different ethnicities within the population. We saw how that could be easily implemented with an empirical distribution in any logic. The open population model further allowed us to experiment some with events. So we had events going on within that population associated with the immigration process, and we saw how those events could be set on a fixed schedule to go off at separate times. So on a fixed set of times over duration, or according to a sorting condition. So we were exposed to the basics of any logic events. Later, we came back and we took a look in a little bit more detail at one specific type of event supported by any logic that goes beyond the capabilities of that normal event object, and that was a dynamic event. The terminology being a little bit confusing. It's dynamic not in the sense that it's over time, but dynamic in the sense that the conditions under which it's to be launched, the parameters for it that tell it what to do, and the timing at which to do that is not pre-specified in the model, but it's specified on the fly while the model's running. And we later saw how we could use dynamic events to capture processes where, the occurrence of one event, say, will trigger another event a certain amount of time later. The occurrence of an appointment at a given time, and that appointment wrapping up in a certain contingent way, will trigger a scheduling of another appointment, or the conception associated with deer mating will trigger a birth event for a deer to occur some period of time in the future. Dynamic events are particularly powerful because we can, at the time that we're going to schedule them, at the time we're going to say, we know that we want an event to go off 3 months from now, we can pack up all the information we need to make that event happen at the requisite time. So we don't have to worry about keeping that information around in some other way. It's packed up together with the event. And that's powerful. It'll presage a little bit something we may see today, if not, then by tomorrow, which are dynamic parameters in any logic, which are a very powerful but underappreciated mechanism within the any logic context. So we did get to see this open population model, which captured a number of processes. Later, we went on and we saw how we could weave in two mechanisms, which I'd say are also underappreciated but readily accessible within any logic, which is the capacity to capture distinct identifiers, sort of the equivalent of a social security number in the States, a social insurance number in Canada, a number that's doled out to a particular individual and never to be reused. We saw how we could capture that easily, but also how we could capture continuous aging on the part of agents. Continuous aging being a process that's occurring implicitly all the time as time advances. We simply need to record the birth time of agents, and their age can be inferred from that. And we additionally saw how we could impose time-varying hazard rates, time-varying probability densities of transition from one state to the other, a chance per unit time of transition from one state to the other that varies over time according to an agent's state, say according to their age, using table functions. Such and such an age, what's their chance per year of dying, uptaking cigarette smoking, developing diabetes, or what have you. We wove that in later. It wasn't part of our open population model per se, but it was closely aligned with some of the features of that model. So open populations, dynamic populations, populations which change over time, very readily captured and quite flexible in terms of our representation of them. We noted that the capacity to capture and keep track of one of the biggest risk factors associated with many health conditions in a very, very fine-grained way. And so it allows us to summarize it according to any number of different categorizations, to slice and dice it as needed, and that's a very powerful attribute. Rather than being hardwired that we only have certain age categories, we can use age categories of convenience for our particular needs. This is important, particularly when we compare with empirical data. We may have empirical data that breaks it up in this way, has some statistic on, for children less than 5, such and such, or another statistic which is children in their first 2 years of life, another statistic about people in their 20s, and the ability to slice and dice it in a familiar way is powerful indeed. Okay, so we looked at the open population point, major emphasis yesterday, and really the last piece of the AnyLogic modeling vocabulary, as it were, for agent-based models, was filling in the piece with spatial embedding and mobility. And specifically, we examined the impact of embedding individuals in two primary types of spaces, continuous and discrete spaces. And we noted that there's a third space type, GIS space, where there's a variety of additional information kept beyond the basics of what continuous space supports. Now, when we took a look at continuous mobility, we saw that we could capture agent movement in either a continuous fashion using this move to method, or in a discrete fashion using jump to. So we can move agents, we could sort of teleport them from one place to another with jump to, or we could have them move according to some velocity, which is adjustable, in a move to type fashion. And we examined both a very stylized model just meant to help communicate some of the basic mechanisms, where we have the mouse interacting with people's movement. And then we also looked at a model where people were moving in space between home and either a school or a workplace and circulating in that capacity. Models of mobility are not certainly by no means always needed, but for certain types of research questions, they play an important role. Research questions that involve exposure to spatially situated contexts, point sources, areas which are known to have higher risks associated with the environment. Cases where we wish to simulate contacts not as a presupposed process as imposed by a network, but as an emergent process coming from interactions of agents. And one of the exercises that I provided, the step-by-step tutorials I provided, involves building a model where you have communicating agents who carry a communicable illness, which are transmitted by contact between agents. And it's a very interesting process and can lead to some counterintuitive realizations. So sometimes we wish to think of a contact not as a primal process, not as a process about which we directly make an assumption with in classic mathematical epidemiology, with a parameter C that captures the number of contacts per unit time each person undergoes, not even with a network, which allows you to capture both who you're contacting on a persistent basis and how frequently, but with in a situation where that contact is emergent from mobility processes. So that's a frequent mobility, but there's influences. Each environment, we're exposed to different norms, different attitudes, and proximity to different individuals. So mobility is an important feature, not for all models, but for some. And we saw how it's fairly well supported. We can set agents in motion, and they'll be moving over time while other agents are moving all simultaneously. So we saw those two examples associated with continuous mobility, and then we took a brief look at a discrete space example, the Schelling segregation model, and two variants of it. One implemented in discrete time, where you had steps going on in a very regular way. The entire model was updating in lockstep, and which is a very common pattern in agent-based models, and was similar to how Schelling, to earlier conceptualizations of the Schelling segregation model. But we also had a situation where we looked at the Schelling model within a continuous continuous time framework, where agents were moving asynchronously. That is, their times of movement was not in lockstep, was not coordinated, but rather each agent would move at a time that saw fit for it. And both those models were making use of a discrete space divided up into to a grid where each cell was either empty or had exactly one agent in it. Agents could move around. There was a number of primitives provided for agents to move to an empty cell or to inquire about who, if anyone, was in the cell in a certain direction of themselves, or to get a list of their neighbors, etc. In this discrete space framework, it's a little bit reminiscent of what you see within a context of NetLogo, where you have these patches, for those familiar with it. But patches are a little bit more flexible than let's put it this way, they make it easy to find a little bit of additional mechanism that requires a little bit more work in any logic to sort of specify the characteristics of each patch. And if there were interest on the part of people during the time we have afforded to us, I'd be glad to talk about how you can very readily deal with that and capture similar information about each patch and its characteristics, whether empty or occupied within any logic context. Finally, for those who stayed for the Java session, we about expressions. We noted that values could be things like integers, 1, 5, -3. They could be double precision values, 3.14159 or 2.71 or what have you. But they could also be references, say, to a person. So I have a value that's a reference to this person, or a reference to main, or a reference to a string. And having such a reference, I could call off to it, ask it to do something for me, interrogate it for information, such as about the length of a string, or I could ask for the person's mother, etc. So those who are here got to see a little bit about the so-called syntax of Java, how you write these formulas that we call expressions in Java, which calculate values. Okay, so that was the final part of the afternoon. So are there any questions about the material covered yesterday, bearing in mind that we're going to have a photographer in here, probably coming in any minute now? Maybe we'll just ask any questions about yesterday's material. Anything I covered yesterday that I could cover right now? Yeah. There is an example, yeah. One of the projects I'm involved when we do that, and it's in fact a more evolved form of that model we looked at with deer moving around. And I think I have a copy. I'm almost virtually certain I have a copy of the more recent model on my computer that I could share with people if there were interest within this group.
Yep.
It's an active research project involving many collaborators, and it wouldn't be something I'd want to sort of put out publicly for reasons of confidentiality with my collaborators, but I'd be glad to share it. Sure.
It'd be great to see how one goes about doing that.
Sure.
Yep, thank you.
Sure, you bet. So that was an AnyLogic 6 formulation. My understanding is that some of the mechanisms in the model were dealing with capturing features of the situation that have been dealt with by, for example, capturing information about being able to zoom in on the map and reasoning about, okay, what's the distance associated with a given visual distance? What does that correspond to in the underlying model? I think that's an area where AnyLogic 7 has now put in place mechanisms to automatically do that, where the model does it manually. So we'd bear in mind that I don't know that the version I have hasn't been updated to incorporate that, although I think it is being updated.
Well, we might have a very simple model that has agents getting screened for colorectal cancer, and we have endoscopy facilities where they would go to get screened in place, and there's age and distance to affect the likelihood of getting screened with.
Sure.
I'm wondering whether we might want to try to quickly put together just a real simple part of that.
Right.
As an example that we can more readily share.
Yeah, I mean, so good question. It bears note that as I've commented, the GIS functionality in AnyLogic builds atop the basic notion of continuous space and so on that you see, and a lot of the features of what you're saying right there could be implemented directly, even absent a GIS map. You could just implement it in space. What you'd be lacking. So, in other words, there's a mechanism in AnyLogic to say how far is this agent from me in a distance metric that isn't directly meters or kilometers. What the GIS functionality would add on top of that is the capacity to reason about, what this really means in terms of your real-world location, right? And I think by extension, although I'd have to double-check the API, sort of, what's my distance from you in meters, kilometers, miles, whatever you want to say. So I think we could do a mock-up that would capture the essential features of that very readily in continuous space. But yeah, it would be kind of interesting if we could make use of the GIS functionality with it, even absent a detailed shapefile to sort of load in.
Is it possible to estimate more readily travel time?
Of AnyLogic that there's explicit. Okay, so I'm not aware of the GIS system specifically having methods for get me from A to B. What I do know is that AnyLogic has a lot of logic associated with that in what's called its markup facility, and this is not something I came with slides on, but the basic deal is that you can, and I could show you examples which illustrate this, the basic features. You can have a map, and this could be a map in the external world or a map of a facility where there are routes shown. So in the external world, this might be roads, right, or biking paths or what have you. In the world of a facility, this might be corridors, right? And you can mark this up, and we have numerous models which show this. And then basically, you could say, bring this agent from this place to this place, and it will route you in some way, according to that network of routes. And it has a shortest path routing algorithm that it uses to sort of figure out your appropriate route, and that's readily supported. My guess is that could be directly applied in the GIS context. The question is, how easy would it be? How trivial is it? What I do know is that within a minor version or two, it's like 7.1 or 7.2, something along those lines, they're planning a major rollout of GIS functionality, which would very materially extend, just incomparably extend, as I understand it, the GIS support. and they're soliciting comments right now on what mechanisms are sought. So in other words, what features would you like to be able to ask the GIS system? So what should they support in it? And I've been asked to opine on that. People in my institution with whom I work who have used GIS functionality are being asked. So if there's interest on your part in getting a certain feature in there into the GIS system specifically, that would be no problem.
Okay, thank you.
Is that helpful?
Yes, very.
Okay. Okay, it looks like the photographer has come in. So, Maria, do you want to be the master of ceremonies? And